We've spent generations dreaming of leaving Earth, building rockets, chasing stars, believing our destiny lies somewhere out there. But what if it doesn't? What if the greatest cosmic secret is that we were never meant to leave at all? So if you want to know the whole story, watch this video till the end and subscribe to the channel. Let's begin. From the moment we first realized the stars were suns like our own, the idea of leaving Earth became more than fantasy. It became destiny. Humanity began to see itself not as a species bound to a single world, but as pioneers merely waiting for the right tools to set sail across the cosmic sea. Science fiction was the spark that fanned this belief into a roaring fire. It told us stories not of impossibility, but inevitability. Writers like Jules Verne and H.G. Wells were the early dreamers, sketching the first blueprints of interplanetary travel long before rockets existed. Verne's From the Earth to the Moon imagined a world where humans could shoot themselves skyward in a colossal cannon. Crude, yes, but visionary. Wells's The War of the Worlds flipped the script, showing that the universe might not welcome us as heroes, but see us as invaders or prey. And yet, even those dark stories carried a single, shimmering message: that space was reachable, tangible, and real. By the 20th century, cinema took those dreams and gave them light, color, and motion. Stanley Kubrick's 2001. A Space Odyssey redefined what space meant. Not just a void, but a cathedral of mystery and evolution. It whispered that our future lay in the stars, that humanity's next great leap would be cosmic, not earthly. Then came Star Wars, which turned space into a playground of adventure, destiny, and rebellion. A galaxy where starships roared like fighter jets and heroes wielded light itself. Every film, every series, from Star Trek to Interstellar, told us the same comforting story: that space was our inheritance, that leaving Earth wasn't a question of if, but when. And while fiction built our imagination, real history made us believe it was within reach. In the 1960s, the space race transformed that dream into something tangible. When Yuri Gagarin orbited Earth, humanity crossed a line no one thought possible. When Neil Armstrong stepped onto the moon, the collective heartbeat of the planet seemed to stop. We were a single species standing on the edge of eternity. The moon landing wasn't just a technological feat, it was a myth come true. We had reached beyond our world and touched another. The optimism that followed was unstoppable. People genuinely believed Mars colonies were just decades away. Textbooks and television specials predicted lunar cities by the 1980s, asteroid mining by the 1990s, and interstellar travel by the 21st century. It seemed obvious that humanity's destiny was upward and outward. The Earth was our cradle, but not our home forever. Or so we thought. The dream of leaving was not just scientific, it was spiritual. It symbolized transcendence, the ultimate triumph of human ingenuity over nature itself. Even as decades passed and progress slowed, the dream persisted. Films like The Martian reignited it, making survival on Mars seem not only plausible, but heroic. Elon Musk spoke of making humanity multiplanetary, echoing the same idealistic flame that once burned in the hearts of those who watched the Apollo missions. Private companies joined the chorus: SpaceX, Blue Origin, Virgin Galactic, promising that the stars were no longer distant, but the next frontier of human civilization. The message remained clear: leaving Earth was not only possible, it was inevitable. But what none of these stories, missions, or promises prepared us for was reality. For all the progress, for all the imagination, one stubborn truth lingered. Since the last Apollo mission in 1972, humanity hasn't ventured beyond the moon's orbit. half a century of technological advancement, and still, our presence in space remains tethered to the safety of our home planet. We've sent robots, probes, and telescopes beyond imagining, but no human has gone farther than that first small step in lunar dust. And that pause, that quiet absence of progress, tells a story more sobering than any fiction. It reminds us that the stars, however bright they seem, remain impossibly far, not just in distance, but in danger, in difficulty, in cost. The space dream, as beautiful as it is, has always been built on the assumption that what we imagine must one day become what we achieve. Yet, the universe doesn't bend to imagination. It bends to reality. And reality, as we'll soon see, is far harsher than any science fiction ever dared to show. The golden optimism of the 20th century made us believe that space was our destiny. But as the decades rolled on, we began to understand something more humbling. Space is not a welcoming frontier. It's not a vast playground waiting to be explored. It's an abyss, silent and merciless, indifferent to our survival. The stories told us that humanity could adapt to anything. But what if, instead, the truth is that we can't? And that's where our dream meets its first real test. Not in technology, not in courage, but in distance itself. Because before we can conquer other worlds, we must face a reality so immense, so utterly beyond human scale, that even our boldest visions start to crumble in comparison. For all our dreams of cosmic expansion, the truth hits harder than the silence of space itself. Humanity has not ventured beyond the moon in more than half a century. In fact, the farthest any human has ever traveled from Earth remains roughly 400,000 kilometers, the distance to our lunar neighbor, achieved by the Apollo astronauts between 1968 and 1972. Since then, not a single human being has crossed that invisible boundary again. The space shuttle stayed in low Earth orbit. The International Space Station orbits a mere 400 kilometers above our planet, closer than many commercial airliners travel in a single day's worth of cumulative mileage. It's as if we took one cautious step into the ocean of space, and then quietly retreated to the shore. In the decades following Apollo 17, the world expected more. Mars missions, lunar bases, spacecraft voyaging deeper into the solar system with human crews aboard. But instead, our ambitions stalled. The towering Saturn V rockets that once carried humans to the moon became museum pieces. Budgets were cut, priorities shifted, and humanity's eyes, once turned toward the stars, drifted back toward the ground. The truth is, the space race was not just a triumph of science. The United States raced to the moon not to explore the cosmos, but to prove dominance over the Soviet Union. When that goal was achieved, the momentum evaporated. The dream outlasted the reason. And yet, this stagnation matters deeply. Because our lack of progress beyond the moon isn't merely a logistical issue, it's a mirror reflecting our limitations as a species. Despite all our technology, all our knowledge, and all our bravado, we are still bound to Earth by gravity, biology, and vulnerability. The moon was humanity's greatest achievement, but it also revealed the thin, perilous thread upon which all our spacefaring ambitions hang. Every step those astronauts took on the lunar surface depended entirely on Earth, its resources, its air, its protection. If anything went wrong, there was no backup plan, no second chance. In the half-century since, our robotic explorers have gone far. Mars rovers, probes to Jupiter and Saturn. Even a spacecraft that has touched the edge of interstellar space. Machines can endure what we cannot. They do not need oxygen, food, gravity, or comfort. They do not feel fear or loneliness. But humans are different. fragile, emotional, limited by biology. For all our intelligence, we are still tethered to the environment that shaped us. Every heartbeat depends on a delicate balance of air pressure, warmth, and chemistry, conditions that exist nowhere else we've yet found. It's easy to think that our absence beyond the moon is simply a matter of money or willpower. But the truth is, space itself is unimaginably hostile. Beyond Earth's magnetic field, cosmic radiation bathes everything in deadly energy. Temperatures swing hundreds of degrees between light and shadow. There is no air, no water, and no protection from micrometeoroids traveling faster than bullets. Every meter you travel away from Earth is a step into an environment that wants you dead. That's why the International Space Station, despite orbiting safely above Earth's atmosphere, is still close enough to be rescued if something goes wrong. It's why the moon remains the farthest we've dared to send human life. It's not just about reaching, it's about surviving. We've learned that going into space is one thing. Staying there is another entirely. The sobering reality is that the moon landings were not the beginning of a grand era of exploration. They were the peak of it. Humanity's greatest leap may have been a single moment in history, not the start of an endless climb. And that matters because it reshapes how we view ourselves. The Apollo missions once made us believe that progress was inevitable, that technology and ambition alone could conquer any frontier. But the decades that followed proved that even our greatest triumphs can plateau, that even the boundless dream of space can stall against the cold wall of reality. The significance of this stagnation goes beyond technology. It's philosophical. It challenges the narrative that humanity's destiny is among the stars. Perhaps, instead, our destiny is to understand the stars, not to inhabit them, to explore them through the eyes of our machines rather than the steps of our feet. The fact that we've remained so close to Earth for so long is not a failure. It's a sign of how extraordinary our one successful journey truly was. Still, the question lingers. If the moon was once within reach, why haven't we gone farther? Why, with all our advancements, do we remain bound to our planet's gravity well? The answer begins with the most relentless obstacle of all, the distance itself. Because in the grand scale of the universe, even our closest neighbors are unimaginably far away. And every kilometer between them is a reminder of how small we truly are. If the moon feels close enough to touch, the rest of the cosmos quickly reminds us just how vast and unforgiving the universe truly is. Distance is the first and perhaps greatest enemy of any dream to leave Earth. We often speak of space as a place we can go to, as if Mars or Jupiter were simply destinations on a map. But in reality, they're so far away that our human sense of scale breaks down completely. Space isn't empty distance. It's infinity spread in every direction. Consider this. If you could somehow drive to the moon in your car, traveling at 100 kilometers per hour without stopping, it would take you about 160 days, nearly half a year of non-stop driving through absolute darkness. But that's just the moon, our next-door neighbor in cosmic terms. Now, stretch that distance to Mars, the most reachable planet for human colonization. Depending on the orbits, Mars can be anywhere from 55 million to 400 million kilometers away. If you tried to drive there at the same 100 kilometers per hour, you would arrive in roughly 63 years. If you somehow survived the void, the radiation, and the complete lack of fuel stops along the way. Flying doesn't make it much better. A modern passenger jet cruising at 900 kilometers per hour could reach Mars in around 7 years. Again, assuming you could even fly in the vacuum of space, which of course you can't. And walking? Forget it. A person walking at a steady pace of 5 kilometers per hour would take more than 1,300 years to reach Mars at its closest point. It's absurd, almost comedic, but it's also sobering. We've grown up with maps, with continents and oceans we can cross in hours. The human brain is simply not built to comprehend scales this massive. Even light, the fastest thing in the universe, struggles to make space feel close. Light from the moon reaches Earth in just over 1 second. But light from the sun takes over 8 minutes to arrive. Light from Mars can take between 4 and 20 minutes, depending on its position. When we send commands to our rovers, there's no instant feedback. They are, in effect, operating in the past. That delay alone illustrates how isolated these worlds are from us, even when viewed through the lens of our most advanced communication technology. And the farther you go, the more the concept of distance becomes meaningless. Jupiter, the largest planet in our solar system, sits about 778 million kilometers from Earth on average. A commercial airplane would take more than 900 years to reach it. Saturn is nearly twice that far. And Pluto? If you boarded a modern jet and flew non-stop to Pluto, you wouldn't live to see the halfway point. It would take more than 8,000 years. That's longer than all of recorded human history. We like to imagine our solar system as a neighborhood, but in truth, it's more like a vast desert with a few lonely oases scattered across billions of kilometers. Between those oases lies a wilderness so vast that no fuel tank could span it, no spacecraft could resupply itself within it, and no human could endure the journey without extraordinary protection. Even the fastest spacecraft ever built, NASA's Parker Solar Probe, travels at over 600,000 kilometers per hour, yet it would still take nearly 7 months to reach Mars under ideal conditions, and more than 6,000 years to reach the nearest star. These distances are not just numbers, they are barriers of existence. Every kilometer farther from Earth is another layer of difficulty, more fuel, more energy, more risk. The farther we go, the less margin for error exists. Communication delays increase, repairs become impossible, and rescue becomes a fantasy. Imagine driving across a continent where one flat tire could kill you, where your car cannot stop, and where the nearest gas station is hundreds of millions of kilometers away. That's deep space travel in a nutshell. Even if we mastered propulsion, even if we could build engines that traveled at a significant fraction of the speed of light, we'd still be bound by scale. The nearest star system, Alpha Centauri, is about 4.37 light-years away. That means even traveling at the speed of light, which no known material object can do, it would take over 4 years to get there. At our current fastest speed, it would take more than 70,000 years, longer than the entire span of human civilization. This isn't to say the dream is foolish, only that it's far more fragile than we let ourselves believe. The distances between worlds are not just physical gaps. They are gulfs of energy, time, and endurance. Each leap away from Earth multiplies the danger, the cost, and the isolation. The stars we see at night may seem close, twinkling as if only a breath away, but every one of those lights is separated from us by a distance so enormous it's measured in years of light itself. And that distance has consequences. It's not just an obstacle to travel, it's a challenge to our very concept of human continuity. How do you sustain a civilization that takes years to send a message to its neighbors? How do you maintain a sense of home when the place you came from fades into a dot of light behind you? The farther we go, the less we can depend on the systems, supplies, and support of Earth. And that realization brings us to the next unavoidable truth. Even if we could bridge those cosmic distances, we'd still have to face the staggering cost of simply getting off the ground in the first place. Because before we can conquer the void, we must first overcome our greatest gravitational prison, the energy it takes just to leave. Escaping Earth isn't just about building a rocket. It's about defying one of the most powerful forces in the known universe, gravity. Every object with mass exerts gravity, but Earth's is particularly stubborn. It holds everything, oceans, air, mountains, and us, tightly in its grip. To break free, a spacecraft must reach a speed of 11.2 kilometers per second, or about 40,000 kilometers per hour. That's called escape velocity, and achieving it demands an astonishing amount of energy. To put it in perspective, reaching orbit, not even escaping Earth, just circling it, requires burning through enough fuel to equal the explosive power of small nuclear weapons. Every mission that has ever left this planet has done so in a controlled inferno. What makes this so difficult is the tyranny of the rocket equation. To lift something into space, you need fuel. But that fuel has mass, which requires more fuel to lift it, which adds more mass, which requires even more fuel. It's a vicious cycle that punishes ambition. The larger your payload, the exponentially more energy you need to move it. That's why even the most advanced rockets are mostly fuel tanks. The mighty Saturn V, which took astronauts to the moon, weighed about 3,000 tons at launch, and 85% of that was fuel. By the time it reached space, only a small capsule, about the size of a moving van, remained. Everything else had been burned, jettisoned, or left behind in the void. That's the first limit of deep space travel: inefficiency. We can build rockets powerful enough to reach orbit, and even the moon, but not without burning through staggering amounts of energy. Sending humans to Mars, for example, would require not just reaching orbit, but accelerating millions of kilometers beyond it, and then slowing down to land safely, before having enough fuel to make the trip back. Each step adds exponential energy requirements, each kilogram of cargo multiplying the cost. When we imagine fleets of colonists traveling to other planets, we forget that every liter of water, every bolt, every breath of oxygen would need to escape Earth's gravity first. The cost, both in fuel and energy, becomes astronomical. Even chemical rockets, the kind we've used since the dawn of the space age, are woefully inefficient for interplanetary travel. They rely on burning propellant and throwing it out the back to push forward, a method that's simple but brutally limited. The energy density of chemical fuel just isn't enough. To go beyond Mars, or to sustain long-term missions without constant refueling, we'd need propulsion systems thousands of times more efficient than what we currently have. Scientists have explored alternatives: ion drives, nuclear propulsion, even antimatter engines. But most remain theoretical, or too dangerous, expensive, or impractical for human missions. The energy problem doesn't stop at propulsion either. Once you've escaped Earth, you still need to power everything that keeps you alive: life support, heating, cooling, communication, radiation shielding. Solar power weakens dramatically with distance from the Sun. By the time you reach Jupiter, sunlight is only about 4% as strong as it is on Earth. Nuclear energy might fill the gap, but it brings its own risks: radiation, instability. The farther you go, the more energy every basic necessity requires. The act of survival becomes an unrelenting drain on limited reserves. And energy isn't just a technical issue, it's a human one. Every watt of power used in space must come from something: a battery, a reactor, a solar array. Each must be launched, maintained, and shielded. The International Space Station, for example, depends on massive solar panels the size of football fields just to keep a handful of people alive in low orbit. Imagine scaling that up for an entire colony millions of kilometers away, where repairs would take months or years. Even a single system failure could mean death. The dreamers among us argue that technology will solve these problems, that one day we'll develop engines so efficient and energy sources so powerful that leaving Earth will be as routine as flying across the ocean. But the universe doesn't care about our optimism. The laws of physics remain the same. Mass, energy, and momentum are not negotiable. The deeper we go, the heavier the price becomes. Even with ideal propulsion, even with infinite resources, every journey outward means one more step away from the natural abundance and energy stability of Earth. Here, we are surrounded by sunlight, gravity, magnetism, atmosphere, all the things that sustain life and civilization. Out there, every bit of energy must be brought, created, or stolen from a hostile void that offers nothing freely. It's humbling to realize that our greatest challenge isn't reaching the stars, it's leaving home. Earth's gravity well is a fortress, built not by design, but by nature, holding us in place with invisible chains. And while we've learned to climb its walls for brief moments, launching satellites, sending probes, walking on the moon, every escape costs more than the last. It's as though the planet itself resists our departure, reminding us how dependent we truly are on its warmth, its resources, its gentle pull. And even if we could solve the problem of energy, if we could somehow build ships capable of sustaining long voyages into the dark, the cosmos would still have another invisible enemy waiting for us, one that no amount of fuel can protect us from. Beyond the safety of Earth's magnetic field, an unseen danger permeates every corner of space: radiation. It's silent, invisible, and lethal. And it may be the single greatest reason why, no matter how far we dream, we may never truly escape Earth's embrace. Space looks beautiful from afar, an endless black ocean spangled with stars, serene and eternal. But that beauty hides one of the deadliest realities of all. Space is filled with invisible poison. Beyond the comforting blanket of Earth's atmosphere and magnetic field lies a universe constantly bombarding everything with high-energy radiation. It's not the soft, warming sunlight we know on Earth. It's pure, unfiltered cosmic violence. Gamma rays, X-rays, and charged particles from the Sun and distant galaxies shoot through the vacuum like microscopic bullets, relentless and unstoppable. In the silent darkness between worlds, radiation is not a background condition. It's a storm that never ends. On Earth, we rarely think about radiation because we're protected. Our planet is a fortress, its magnetic field deflecting solar particles, its atmosphere absorbing the worst of cosmic rays. Even in high-altitude flights or at the top of mountains, we're still safe beneath that shield. But the moment a spacecraft leaves low Earth orbit, that protection fades. The invisible armor thins out until nothing stands between human flesh and the raw energy of the universe. Out there, every cell in the body becomes a target. Cosmic radiation comes from two primary sources: solar radiation and galactic cosmic rays. Solar radiation, mostly from solar flares and coronal mass ejections, can spike suddenly, releasing torrents of charged particles powerful enough to fry electronics and cause radiation sickness in minutes. Galactic cosmic rays, on the other hand, come from supernovae, the remnants of exploded stars scattered across the galaxy. These rays are far more energetic and constant, capable of passing straight through metal, bone, and even DNA. Unlike a single burst from the Sun, galactic radiation never stops. It's a ceaseless rain of atomic shrapnel. For astronauts aboard the International Space Station, radiation is already a serious concern, even though they orbit within Earth's partial magnetic protection. They receive doses about 50 times higher than what people experience on the surface. Over long periods, that exposure increases the risk of cancer, heart disease, and neurological damage. But those missions last only months, and the station is close enough for emergency evacuation. Once you go beyond Earth's magnetic field, to the Moon, Mars, or beyond, you're fully exposed. On a journey to Mars, astronauts would face continuous radiation for 6 to 9 months each way, plus additional exposure on the Martian surface, which lacks a protective magnetic field or thick atmosphere. Estimates suggest that a single round-trip mission could expose humans to more radiation than the maximum career dose currently permitted for astronauts. In plain terms, that means such a mission could significantly raise the risk of fatal cancer, DNA mutation, or cognitive decline, even before considering the other dangers of space travel. Shielding against this radiation isn't easy. The most effective materials for blocking high-energy particles are dense, lead, water, or thick regolith. But the heavier the shield, the more energy and fuel are required to lift it from Earth's gravity. That's the cruel paradox. The more protection you need, the more mass you must carry. And the more mass you carry, the harder it becomes to even reach space. Engineers have proposed clever solutions: electromagnetic fields, hydrogen-rich plastics, even shelters built from Martian soil. But so far, none have proven capable of completely safeguarding the human body during long-duration missions. Even the spacecraft themselves are vulnerable. Radiation degrades electronics, erodes materials, and interferes with communication systems. Over years, it can fry sensors and corrupt data, forcing costly redundancy and constant maintenance. For human missions, it's not just about equipment, it's about biology. Radiation doesn't simply damage tissue, it changes it. It breaks molecular bonds, alters cellular structures, and mutates DNA. It can lead to cataracts, immune suppression, fertility issues, and cognitive decline. In deep space, every second of exposure is a gamble with biology. Imagine being surrounded by an invisible storm that passes through walls, metal, and your own skin. You can't see it, smell it, or feel it, yet it's constantly rearranging the atoms in your body. That's the reality of space travel beyond Earth's protective bubble. And unlike the mechanical problems of propulsion or fuel, this is a challenge of biology and physics, one that no amount of optimism can ignore. We've already seen glimpses of this threat in those who've gone before. Apollo astronauts reported seeing flashes of light even when their eyes were closed, cosmic rays passing directly through their retinas. It's a haunting reminder that, outside our atmosphere, we're walking through a universe that doesn't care whether we survive. For all the talk of Mars colonies and interstellar voyages, radiation remains a silent barrier, one that technology has yet to meaningfully overcome. Some suggest that future humans might evolve to withstand radiation, or that genetic engineering could fortify our cells. Others imagine enormous spacecraft with built-in magnetic shields or thick water walls. But each of these ideas remains theoretical, costly, and decades away from realization. The universe doesn't wait for our technology to catch up. The radiation is already there, and it will be there long after we're gone. This invisible threat reveals something fundamental. Earth isn't just our home, it's our armor. Its magnetic field is a natural shield, a gift we take for granted every second we live. Out there, in the emptiness between worlds, we have no such protection. We are naked in a storm of cosmic energy that neither sees nor pities us. And even if we could protect our bodies from radiation, if we somehow found a way to survive years of exposure, we would still face another, equally unforgiving truth. Our bodies themselves are not built for the weightless void we're so desperate to conquer. Gravity, the same force we struggle to escape, is also the one that keeps us whole. Without it, the very structure of our bodies begins to unravel. In the weightless silence of space, human bodies begin to forget themselves. The same force we fight so hard to escape, gravity, is also the invisible architect of everything we are. Our hearts, our bones, our blood, even the way our cells divide, all evolved under Earth's constant pull. The moment we leave it behind, the human body begins to unmake itself, piece by piece. Zero gravity isn't freedom. It's a slow unraveling of the biological design that ties us to home. At first, it feels like liberation. Astronauts describe floating through spacecraft as almost magical, like living in a dream where movement requires only thought. But within days, that magic turns to strain. Muscles, no longer needed to fight gravity, begin to weaken. Legs lose tone, backs lose strength, and the cardiovascular system grows lazy. On Earth, every heartbeat pushes blood upward against gravity's pull. In orbit, that resistance disappears, and blood shifts toward the upper body and head, causing puffy faces, nasal congestion, and increased pressure on the eyes. The heart doesn't need to pump as hard, so it gradually shrinks. Upon returning to Earth, astronauts often find themselves dizzy, weak, and unable to stand. Their bodies have literally forgotten how to live under gravity. Bone loss is even more alarming. In microgravity, bones no longer bear weight, and the cells that maintain them, osteoblasts and osteoclasts, fall out of balance. Astronauts lose roughly 1% of bone density per month in space, comparable to an elderly person with severe osteoporosis. On a mission to Mars, which could last more than 2 years, that means potentially catastrophic skeletal weakening. Even with intense daily exercise, the losses can't be fully prevented. Imagine returning to a world with gravity only to find your bones too brittle to support you. Eyesight, too, begins to fail. A condition known as spaceflight-associated neuroocular syndrome, SANS, affects more than half of long-term astronauts. With fluids shifting toward the head, pressure builds behind the eyes, flattening the eyeball and distorting vision. Some astronauts have returned with permanent eyesight changes, a price paid for seeing the stars more closely than most ever will. Scientists still don't fully understand the mechanism behind it, which makes prevention difficult. Space doesn't just tire the body, it alters the very way it perceives the world. Then there's the brain. Studies on astronauts have shown structural changes in the brain after extended missions. The fluid dynamics of cerebrospinal fluid shift, grey matter distribution changes, and cognitive performance can fluctuate. The brain adapts to microgravity, but at a cost. Spatial orientation, balance, and reaction time all degrade. In deep space, far from any aid, even a brief lapse in judgment could be fatal. And these are only the physical effects. The immune system weakens, wounds heal more slowly, and radiation exposure, compounded by microgravity, accelerates aging and cellular damage. Muscle mass can be rebuilt, and bone density can slowly recover once back on Earth. But years in microgravity might cause damage that never fully heals. The human body evolved to function perfectly under one set of environmental conditions. 1 atmosphere of pressure, 9.8 meters per second squared of gravity. And removing those conditions unravels the equilibrium of millions of years of evolution. We've tried to fight back. Astronauts aboard the International Space Station spend up to 2 hours a day exercising, tethered to resistance machines designed to simulate gravity's pull. They use specialized treadmills and cycling systems to keep their hearts and muscles active. But even this regimen merely slows the degradation. It doesn't stop it. Artificial gravity, rotating habitats that use centrifugal force to mimic gravity's effects, has been a staple of science fiction for decades. But in reality, it's a complex engineering nightmare. Building a spinning structure large enough to generate usable gravity without inducing disorienting forces or mechanical failure is far beyond our current capabilities. Some propose shorter missions or frequent rotation between Earth and orbit, but deep space travel doesn't allow such luxury. A journey to Mars, for example, would mean months of continuous microgravity, followed by a landing on a planet with only 1/3 of Earth's gravity, not enough to reverse the damage. Returning home afterward could leave astronauts physically broken, unable to even walk after years in low gravity. The more we imagine permanent colonies on other worlds, the clearer it becomes. Our bodies were made for Earth, and they know it. This biological dependency is one of the most overlooked yet insurmountable barriers to human colonization of space. We can build rockets to overcome gravity, but we cannot yet rebuild ourselves to live without it. The cost of leaving Earth isn't just technological, it's anatomical. Space doesn't merely challenge us, it dismantles us. It takes the systems honed by evolution and exposes how fragile they truly are outside the narrow comfort zone of our home planet. And if microgravity erodes the body, isolation erodes the mind. Even the strongest astronauts, trained, tested, and psychologically prepared, have reported the mental toll of endless darkness, confinement, and silence. Because space doesn't only strip away our biology, it strips away the familiar, the sky, the air, the sounds of life. In the endless black, cut off from Earth for months or years, the human mind begins to turn inward, and not always in ways that can be controlled. Out in the black, where there is no horizon and no wind, the human mind begins to bend. Space is the ultimate isolation chamber, vast beyond measure, yet suffocatingly small inside a spacecraft. For all its wonder, the reality of living beyond Earth is psychological pressure distilled to its purest form. The further we go, the more distance becomes not just physical, but emotional, and it's there, in that silent, infinite emptiness, that the mind begins to struggle against itself. On Earth, even in solitude, we are never truly alone. The air hums with life, the distant sound of traffic, the rustle of trees, the murmur of voices. Our senses are constantly fed by the presence of other living things, by the pulse of a world that feels alive. In space, that background vanishes. There is no sound, no scent, no breeze. The view outside is beautiful, but it is also unchanging, endless black, dotted by unreachable stars. The closest sign of life is a fading blue marble, slowly shrinking in the window. Astronauts have described this as both awe-inspiring and terrifying, a duality that gnaws at the psyche. For the first few days, there's wonder, the sight of Earth rising over the moon, the weightless freedom, the sense of doing something no human should be able to do. But as the weeks stretch into months, the novelty fades and reality sets in. Every wall, every sound, every face becomes familiar to the point of claustrophobia. There's no escape from the constant hum of machinery or the awareness that outside those thin metal walls is instant death. The human brain evolved in a world of cycles, day and night, seasons, weather. These rhythms anchor our mental stability, giving us a sense of time and continuity. Space strips that away. The sun rises and sets every 90 minutes aboard the International Space Station. Days blur together into a perpetual loop of artificial light and darkness. The body's internal clock begins to drift, disrupting sleep, hormones, and mood. Astronauts report insomnia, irritability, and depression. The longer they remain, the more fragile their mental state becomes. Then there's the weight of isolation, not just from the world, but from humanity itself. Imagine being months away from Earth, knowing that if something goes wrong, there is no rescue, no fallback, no second chance. Communication delays of several minutes mean that every conversation with home feels distant and disconnected. You can't call for comfort, you can only wait. Over time, that distance erodes the sense of belonging. The mind starts to turn inward, and in that silence, fears echo louder than ever. Even on the relatively short missions aboard the ISS, astronauts experience tension and emotional fatigue. Group dynamics become strained. Small disagreements can feel monumental when there's nowhere to go and no one new to talk to. Every word carries more weight because it has nowhere to dissipate. NASA psychologists have compared it to being locked in a small room with the same people for months, except that outside the door isn't freedom, but the void. It's not just loneliness, it's existential pressure. Long-duration isolation changes perception itself. Some astronauts describe a phenomenon known as Earth out of view anxiety, a deep primal discomfort that arises when Earth is no longer visible. Our planet is more than just home. It's an emotional anchor. Seeing it, that familiar blue sphere, reminds us of safety and meaning. When that image fades into a distant dot, something in the psyche breaks. The vastness of space, once awe-inspiring, becomes suffocating. The silence grows louder. The stars stop feeling like destinations and start feeling like walls. NASA and other space agencies have spent decades studying how to prepare humans for this kind of isolation. They've run analog missions in Antarctica, underwater, and in simulated Mars habitats in the desert. Environments designed to mimic the isolation, confinement, and sensory deprivation of space. In every case, the results are clear. Humans can adapt, but only for a time. Prolonged isolation leads to cognitive fatigue, emotional detachment, and in some cases, hallucinations. The brain, deprived of normal sensory and social input, begins to generate its own phantom sounds, false sensations, imagined presences. Now imagine that lasting not for months, but for years. Imagine a crew on its way to Mars, confined in a metal shell no larger than a small house, staring at the same walls, breathing the same recycled air, speaking to the same few voices every single day. The delay in communication with Earth stretches to 20 minutes each way. Real-time conversation becomes impossible. Every message home is an echo sent into the void, answered long after the moment has passed. In that environment, even the strongest minds begin to fray. The greatest threat to long-term space missions may not be mechanical failure or radiation. It may be the slow, invisible corrosion of the human mind. We are social creatures, hardwired for connection, novelty, and sensory variety. Space offers none of these. It demands stillness, sameness, silence. It asks us to stare into infinity and find meaning there, a task that few could endure without breaking. And yet, even if the mind could adapt, even if humans could endure the loneliness and confinement of interplanetary travel, we would still be bound by another, equally fragile limitation: the systems that keep us alive. Because in space, survival isn't just about endurance or willpower. It's about the delicate balance of air, water, and warmth, systems that are finite, fallible, and entirely dependent on Earth. And if those systems fail, no strength of mind can save you. Life in space depends on an illusion. The illusion that we can bring a piece of Earth with us wherever we go. Inside a spacecraft, every breath, every drop of water, every heartbeat relies on machines designed to mimic what our planet does naturally and effortlessly. On Earth, oxygen is replenished by plants, water cycles through clouds and rivers, and waste breaks down into the soil. In space, all of that must be manufactured, maintained, and powered, constantly, without fail. And the further we travel from Earth, the more impossible that illusion becomes to sustain. Life support systems are humanity's most intricate form of defiance. They are artificial ecosystems built inside metal shells, fragile bubbles of habitability floating through the void. The International Space Station, for example, is an engineering marvel, a laboratory orbiting at 400 kilometers above Earth where astronauts live for months at a time. But every moment of their survival is a balancing act. Air is recycled through filters that remove carbon dioxide and humidity. Water is purified from sweat, breath, and even urine. Food is prepackaged and shipped from Earth on resupply missions. Nothing inside the ISS is natural. Every system depends on constant electricity, precise calibration, and regular maintenance. A single malfunction could mean suffocation, poisoning, dehydration, or worse. Even here, only a few hundred kilometers away, maintaining these systems is a full-time job. Engineers on the ground monitor every fluctuation in pressure, temperature, and air quality. When something breaks, spare parts are flown up from Earth, a luxury that won't exist on Mars or beyond. In deep space, there is no resupply. Every failure would have to be fixed with what's already on board. A clogged filter, a power outage, or a leaking valve, problems that seem trivial on Earth, could spell disaster millions of kilometers away. The fragility of life support systems becomes even more daunting when you consider their energy demands. Recycling air and water, maintaining temperature, filtering waste, generating light for plants, powering computers, and running propulsion systems all require immense amounts of energy. On Earth, energy is abundant and easily replaced. In space, every watt is precious. Solar panels work well in orbit, but their efficiency drops sharply as you move farther from the Sun. By the time you reach Mars, sunlight is about half as strong as on Earth. Beyond Jupiter, it's practically useless. Nuclear reactors can provide power, but they're heavy, complex, and dangerous, and one failure could irradiate an entire crew. Even the most efficient closed-loop life support systems are imperfect. Over time, waste builds up, filters wear out, and chemicals degrade. The more you recycle, the less pure the recycled resources become. Nothing is truly infinite. Entropy always wins. NASA's most advanced environmental control and life support system, ECLSS, aboard the ISS, can recycle around 90% of the station's water and reclaim oxygen from carbon dioxide. But that last 10% still depends on resupply from Earth. Over long missions, that shortfall becomes a death sentence unless constantly replenished. On a planet like Mars, where the atmosphere is mostly carbon dioxide and surface temperatures can drop below -100 degrees Celsius, life support systems would have to operate continuously just to keep humans alive for a few minutes outside their shelters. Each habitat would be a sealed container, a self-contained ecosystem vulnerable to every failure mode imaginable. One torn seal, one power loss, one miscalculation in chemical balance, and the entire colony could be lost. The idea of terraforming Mars, turning it into a second Earth, is a dream that ignores how impossible even small-scale sustainability is with current technology. We can't yet sustain a completely closed life system for more than a few months without help from Earth. Expecting one to function indefinitely, millions of kilometers away, is fantasy. And it's not just about the systems, it's about the people running them. Every astronaut must become part engineer, part scientist, part caretaker. They must understand every system that keeps them alive, because if something goes wrong, they are the only ones who can fix it. Every day becomes a ritual of maintenance, checking oxygen levels, scrubbing carbon dioxide, inspecting filters, managing power consumption. Living in space isn't freedom, it's labor, constant, meticulous, and exhausting. Even with all that effort, uncertainty lingers. What happens when a valve jams? When a filter fails? When a chemical reaction goes wrong in a closed system with no fresh supplies? The smallest mechanical failure can cascade into catastrophe. In 1997, the Russian space station Mir experienced a fire that filled the cabin with smoke. It took minutes to extinguish, minutes that felt like eternity in an environment where every breath could be your last. And that was in low Earth orbit, where rescue was theoretically possible. In deep space, there is no margin for error. Life support systems reveal a haunting truth about our species. We are not built for independence from our planet. Earth's ecosystems do more in a single moment than all our technology can achieve in a lifetime. Our air, water, and food systems are gifts we've barely learned to understand, let alone replicate. Space travel forces us to see how dependent we are on the delicate balance we take for granted. We are sustained by a biosphere billions of years in the making, one we cannot yet reproduce, no matter how advanced our machines become. And even if we could maintain these fragile systems indefinitely, if we somehow built perfect, self-sustaining habitats, we'd still have to ask whether the place we're fighting to survive in is even worth the effort. Because the closest candidate for a second home, Mars, is not a cradle of opportunity or adventure. It's a wasteland, frozen, toxic, and unforgiving. And the dream of turning it into another Earth may be the most dangerous illusion of all. Mars has always been the golden promise of our cosmic imagination, the next great frontier, the backup Earth, the planet that might one day cradle a second branch of humanity. Through telescopes and science fiction, we've painted it as a world of adventure and potential, a place where red deserts would one day bloom with green. We've dreamed of cities under domes, colonies carved into canyons, explorers walking beneath twin moons. It's easy to fall in love with that image, the red planet, fierce and lonely, waiting for us to give it life. But that vision is a mirage. The real Mars is not a home in waiting. It's a graveyard of habitability, a frozen desert that kills without mercy. Mars is beautiful only from a distance. Up close, it's a nightmare of extremes. The temperature averages around -63 degrees Celsius, but near the poles, it can plunge below -120 degrees Celsius, cold enough to freeze carbon dioxide into solid dry ice. The air itself is poison. It's 95% carbon dioxide, less than 1% oxygen, and thin enough that even if you somehow breathed it, your lungs would rupture from the pressure. Standing on the surface of Mars without a pressurized suit would mean death within seconds, not from freezing, but from suffocation as your blood began to boil in the low pressure. Even inside a sealed habitat, survival would be a constant fight against the planet's hostility. And then there's the dust. Martian dust is one of the most insidious dangers on the planet. It's not like sand on a beach. It's a fine, powdery substance made of sharp, microscopic particles of iron oxide and silica that cling to everything. The Apollo astronauts brought back lunar dust that tore through seals, irritated their lungs, and destroyed machinery. Mars dust is worse. It contains perchlorates, toxic chemicals that interfere with thyroid function and can cause severe poisoning if inhaled or ingested. Every time you open an airlock, that dust comes inside. It clogs filters, coats equipment, and settles into every surface. Over time, it would slowly contaminate living quarters, air systems, and even food sources. Radiation is the next invisible enemy. With no global magnetic field and only a wafer-thin atmosphere, Mars offers no shield from cosmic rays or solar radiation. Standing on the surface, you'd receive hundreds of times more radiation than on Earth. A slow but steady dose that would increase the risk of cancer and neurological damage over time. Habitats would need to be buried under meters of Martian soil just to provide adequate protection. Living on Mars would mean living underground, in constant twilight, far from the romantic images of open domes and sunlit cities. Then there's the dust storms, vast, planet-wide tempests that can last for months. They darken the sky, block sunlight, and strip solar panels of energy. The atmosphere on Mars is thin, so the winds wouldn't knock you over, but the constant dust would choke engines, cover sensors, and plunge colonies into freezing darkness. For any settlement dependent on solar power, a dust storm could mean total blackout. On Earth, storms pass. On Mars, they can linger so long that they test the limits of survival. Water, too, is a cruel illusion. Mars has ice, plenty of it, but most lies locked beneath the surface or at the poles, far from areas suitable for settlement. Extracting it requires enormous energy and infrastructure. And even if we could melt it, purify it, and store it, water is only one piece of the puzzle. Food would need to be grown in pressurized environments using recycled waste. Every bite, every sip, every breath would depend on fragile systems that could fail with one mistake. Yet, despite this reality, Mars continues to be romanticized as humanity's destiny. Movies like The Martian or Total Recall turn survival there into a story of ingenuity and courage. And while those stories inspire us, they simplify the truth. Real life on Mars wouldn't be cinematic or heroic. It would be monotonous, dangerous, and claustrophobic. It wouldn't be a place of discovery. It would be a place of maintenance, of constant vigilance. Colonists wouldn't be explorers gazing at alien sunsets. They'd be technicians keeping themselves and their machines from dying another day. We love to imagine Mars as a second chance, a reset button for humanity if Earth falls. But Mars is not a sanctuary waiting for us. It's a frozen tomb. No oxygen, no magnetosphere, no rain, no sound of life. Its red hue isn't warmth, it's rust. The planet is literally oxidized, its surface a testament to billions of years of sterility. We can land there, walk there, maybe even stay there for a time, but we will never belong there. Not in any natural or sustainable sense. Some argue that we can make Mars more like Earth through terraforming, melting its ice caps, thickening its atmosphere, and planting life. But even this dream begins to crumble under the weight of physics and time. The energy required to warm an entire planet is unimaginable. It would take centuries, perhaps millennia, to even make the atmosphere breathable. And even then, the lack of a magnetic field would mean constant atmospheric loss to solar winds. Mars wouldn't stay terraformed. It would decay back into the dead world it is now. The truth is, Mars was once more like Earth. Rivers, lakes, perhaps even oceans flowed across its surface billions of years ago. But the planet lost its core heat, its magnetic field faded, and its atmosphere was stripped away by the sun. What remains is a world that shows us what happens when a planet dies. Mars isn't our future. It's a warning, a glimpse of what could happen if we destroy the delicate balance that makes Earth so rare and alive. For all our talk of colonization, survival on Mars would always be temporary, dependent on endless shipments of supplies from Earth, on fragile systems and constant maintenance. It would be a foothold at best, not a home. The dream of a second Earth is not just optimistic, it's delusional. Mars doesn't need us, and we cannot exist without Earth. And yet, some cling to the idea that if we cannot live there as it is, we can change it, shape it, mold it, make it ours. But that next dream, the dream of terraforming, is not just impractical, it's the ultimate expression of human arrogance. The belief that we can re-engineer a planet from the ground up. Terraforming, the dream of transforming alien worlds into Earth-like havens, has captured human imagination for nearly a century. It's the ultimate fantasy of control, the belief that with enough time and technology, we could breathe life into the lifeless. It's in the books of Ray Bradbury, the films of Hollywood, the bold speeches of visionaries like Elon Musk. The idea is simple: take a dead planet like Mars and make it live. But the simplicity of that vision hides the brutal truth. Terraforming is not just beyond our reach. It might be beyond the reach of nature itself. Turning Mars, or any planet, into another Earth would take not decades, not centuries, but thousands, perhaps millions, of years, if it's even possible at all. To terraform a planet, you first need to give it an atmosphere thick enough to trap heat and support liquid water. Mars has an atmosphere less than 1% as dense as Earth's, and it's almost entirely carbon dioxide. For humans, that's poison. For plants, it's barely enough to photosynthesize effectively at such low pressure. The most common proposal is to release the carbon dioxide frozen in the planet's polar ice caps and soil to create a greenhouse effect, warming the planet and thickening the air. In theory, this would start a chain reaction. As the temperature rises, more CO2 is released, which traps more heat, and so on. But there's a problem. The numbers don't add up. NASA's own studies have found that even if we used every gram of carbon dioxide available on Mars, we'd only reach about 2% of Earth's atmospheric pressure, far too thin for humans to breathe or for liquid water to remain stable. That means Mars simply doesn't have enough raw material to terraform itself, even with our help. We'd have to import vast quantities of gases from elsewhere, maybe from Venus or comets, or by producing them artificially. Each of those solutions would require unimaginable energy and infrastructure, not just on planetary scales, but interplanetary ones. Let's assume, somehow, we did it. Suppose we warmed Mars, released CO2, and created a thicker atmosphere. It still wouldn't last. Mars lost its atmosphere once already, billions of years ago, and for the same reason it would lose it again. It has no magnetic field. Without a global magnetosphere, the solar wind, streams of charged particles from the sun, would slowly strip away any new atmosphere we created. It's not just a one-time process, it's constant erosion, like trying to build a sandcastle in a storm. Within a few thousand years, maybe less, all that effort would vanish into space. Even if we somehow maintained the atmosphere with technology, massive electromagnetic shields, continuous gas production, or orbital mirrors to heat the poles, we'd still be left with a world hostile to life. Mars's soil is laced with perchlorates and heavy metals toxic to most Earth organisms. Its temperatures would still swing wildly, its radiation levels would remain lethal, and its gravity, only about 38% of Earth's, would permanently weaken human bones and muscles over generations. We could give Mars air, but we couldn't give it gravity. And without gravity, it could never truly become a second Earth. Terraforming advocates often point to Earth's own climate history, how simple organisms once altered our atmosphere over billions of years, turning it from toxic gas into breathable air. But that transformation was driven by an entire biosphere and timescales longer than all of human civilization combined. Expecting technology to replicate that in a few centuries is wishful thinking. Even the most advanced proposals, like using orbiting mirrors to focus sunlight or seeding the atmosphere with engineered microbes, depend on assumptions that remain untested and largely speculative. And then there's the energy problem. To warm Mars by just a few degrees, you'd need to release the equivalent of the energy output of all the nuclear weapons ever built, not once, but continuously for centuries. To generate a breathable atmosphere, you'd need to produce trillions of tons of oxygen, a process requiring either photosynthesis or massive industrial effort. And remember, all of this must happen in an environment that is constantly trying to kill you, using machines that must never fail, powered by energy sources that must never run out. Some propose a more modest approach, terraforming smaller regions instead of the whole planet, creating sealed domes or underground habitats where the air and temperature could be controlled. This is far more achievable, and in truth, it's what most terraforming would look like in the real world. But that isn't making Mars Earth-like. It's just building survival bubbles. Temporary sanctuaries that depend on technology, not transformation. We wouldn't be terraforming Mars. We'd be mechanically simulating Earth, forever at war with the environment outside. And what about the ethics? If microbial life exists on Mars, even the faintest trace of it, terraforming would destroy it. We would be erasing a unique chapter of the universe's story before we even had the chance to read it. Our desire to reshape another planet reveals something deeply human. Our instinct not just to explore, but to dominate, to make the alien familiar. But the cosmos doesn't bend to our comfort. Terraforming assumes that what is foreign must be changed. That instead of adapting to Mars, Mars must adapt to us. That's not exploration. That's conquest. The allure of terraforming is emotional, not practical. It speaks to our fear of mortality, of our planet dying, of our species being confined to one fragile world. It's the ultimate escape fantasy, a belief that no matter how badly we damage Earth, we can always start over somewhere else. But that belief is an illusion. Even if we had the power to re-engineer an entire planet, the time, energy, and resources required would span countless generations. The odds that humanity would survive long enough to see it completed are slim. In truth, terraforming isn't about science, it's about psychology. It's about our refusal to accept limits, our unwillingness to admit that we might belong only to one world. But perhaps the lesson isn't that we should make other planets like Earth. Perhaps it's that we should make Earth less like Mars. Because while we dream of bringing life to other worlds, we're slowly stripping it away from our own. And even if, against all odds, we built the perfect ship, found the perfect fuel, and made a new world bloom, we would still face another inescapable obstacle, our technology itself. For all our progress, the machines that carry us are still bound by physics. The fastest rockets we've ever built crawl through the cosmos at a pace that makes interplanetary travel not just expensive, but glacial. The limits of our technology, propulsion, speed, and endurance, remain the anchor that keeps our dreams tethered to this one blue sphere. When we look at the vastness of space, it's tempting to believe that speed is merely a question of better engines, that someday we'll simply invent a rocket powerful enough to close the unimaginable distances between worlds. But the truth is far less forgiving. Even our fastest and most advanced spacecraft crawl across the cosmic stage compared to the scale of the universe. The technological limits we face are not just challenges of engineering, they are fundamental constraints set by physics itself. No matter how sophisticated our rockets become, we are still trying to light a candle in an ocean. Take the fastest human-made object ever built, NASA's Parker Solar Probe. It travels at an astonishing speed of over 600,000 kilometers per hour, fast enough to circle Earth in just 4 minutes. And yet, at that velocity, it would still take over 6,600 years to reach the nearest star, Proxima Centauri. That's not a typo. Thousands of years. Even Mars, our closest planetary neighbor, takes between 6 and 9 months to reach with current technology. Jupiter, about 5 years. Saturn, 7. Neptune, more than a decade. The distances between planets are so immense that even when moving at tens of thousands of kilometers per hour, space travel feels like crawling through eternity. Chemical rockets, the engines that have carried every human mission into space so far, are built on ancient principles. They burn fuel, create thrust, and push against the vacuum. But they're horrifically inefficient. About 90% of a rocket's mass at launch is fuel, and most of that energy is spent just escaping Earth's gravity. Once in space, the rest is used sparingly because every additional kilogram of fuel adds exponential weight. It's a system that works for short trips, to orbit, to the Moon, to Mars, but not for true interplanetary or interstellar travel. Beyond Mars, the math breaks down. The problem isn't just speed, it's acceleration. To reach higher speeds, you need more energy, but adding more fuel increases mass, which requires even more energy. It's a vicious cycle known as the tyranny of the rocket equation. Every solution we've devised so far is limited by this same equation. That's why interplanetary missions rely on gravity assists, using planet's gravity to slingshot spacecraft faster without burning fuel. It's clever, but slow. It means every voyage must follow precise windows and trajectories, waiting for the perfect planetary alignment, sometimes for years. Scientists have long dreamed of breaking free from these limits. Ion propulsion, for instance, offers efficiency far beyond chemical rockets. Instead of burning fuel explosively, it uses electricity to accelerate charged particles, ions, out of a thruster. This allows spacecraft to gradually build speed over months or years, reaching much higher velocities than chemical propulsion could ever achieve. NASA's Dawn spacecraft, which visited the asteroids Vesta and Ceres, used ion engines successfully. But there's a catch. Ion thrusters produce incredibly low thrust, about the same force as the weight of a sheet of paper in your hand. They can't lift off from Earth, and their acceleration is painfully slow. Over time, they can become fast, but fast still means decades to reach the outer planets, not days or weeks. Other propulsion concepts, like nuclear thermal rockets, promise greater thrust and efficiency. They use nuclear reactions to heat hydrogen and expel it at high speeds, potentially cutting travel time to Mars in half. Yet these designs remain experimental, untested in space, burdened by safety concerns. Even if built, nuclear propulsion faces the same fundamental issue. It's still bound by mass, fuel, and energy limitations. And beyond that lies an even greater obstacle: human tolerance. The faster you accelerate, the more force your body must endure. Pushing people to speeds that could meaningfully shorten interplanetary travel would require not only immense energy, but also physical resilience far beyond what the human body can withstand. Some of the most ambitious proposals push into the realm of science fiction: antimatter propulsion, fusion drives, even light sails powered by giant lasers. Antimatter could, in theory, convert mass to energy with near-perfect efficiency, but creating and storing antimatter is astronomically difficult and dangerous. We can currently produce only nanograms of it, at costs exceeding trillions of dollars per kilogram. Fusion drives, inspired by the same process that powers the Sun, are another theoretical hope. They could provide sustained thrust and enormous energy density. But controlled fusion, even for power plants on Earth, remains unsolved after decades of research. Light sails, like the ones being explored by the Breakthrough Starshot initiative, could push small probes to near light speeds using powerful lasers. But they're only viable for gram-sized payloads, not human beings or colonies. Even if these technologies were developed tomorrow, their deployment would face staggering challenges. Building the infrastructure for them, massive energy sources, orbital construction facilities, fuel depots, and interplanetary maintenance systems, would take generations. Every new technology introduces new failure modes, new risks, new costs. The romantic vision of sleek starships racing between planets ignores the brutal reality. Space is not an ocean to sail, but a desert of nothingness, where every drop of fuel, every atom of air, and every spark of energy must be carried with you or created from scratch. And there's another limit, one not of machinery, but of time. Even if we had engines capable of reaching Mars in a week or Jupiter in a month, the universe itself still enforces a hard ceiling, the speed of light. Einstein's theory of relativity makes faster-than-light travel not just impractical, but impossible, at least with our current understanding of physics. As you approach light speed, your mass increases toward infinity, and the energy required to continue accelerating also approaches infinity. In simpler terms, no matter how powerful our rockets become, there's a universal speed limit that can never be crossed. We are, in every sense, bound to slowness. Our machines crawl, our communications lag, our progress measures itself in decades. And while robotic probes can afford to wait centuries to reach their destinations, humans cannot. Our bodies decay, our resources deplete, our patience wanes. The dream of traveling freely between planets, of turning the solar system into a neighborhood, remains centuries away. These technological limits are not signs of failure, they are reminders of scale. The universe is vast, not because we are weak, but because it is strong. The distances, the energies, the timescales, all exist on a level far beyond the reach of human engineering. We are creatures of a single world trying to defy the architecture of creation itself. And even if someday we manage to build the engines, solve the fuel problem, and finally cross the void at speeds that make interplanetary travel routine, we will still face another, quieter danger, one that has nothing to do with physics and everything to do with dependence. Because even the most advanced colony would still need the one thing no rocket can carry, the endless supply chain of Earth. Every off-world settlement, no matter how advanced, would still depend on the fragile link between home and the void. And if that link ever breaks, so too would everything we built beyond it. Every vision of humanity spreading through the stars, gleaming colonies on Mars, floating cities in orbit, domed habitats beneath alien skies, shares a fatal flaw. None of it can exist without a constant lifeline to Earth. No matter how advanced our technology becomes, every off-world settlement would depend on an unbroken chain of resources, machinery, food, and expertise flowing from our home planet. Space colonization is often sold as the key to human independence, a way to escape Earth's limits. But in reality, it would create the most fragile and dependent civilization in history. Consider how much it takes just to sustain a single person in space. On the International Space Station, every meal, every spare part, every tool, every drop of fresh water that isn't recycled comes from Earth. Even though the ISS orbits a mere 400 kilometers above us, closer than the distance between New York and Washington, D.C., resupplying it is a logistical ballet requiring precision timing, billions of dollars, and international coordination. Rockets must launch perfectly, rendezvous in orbit, and dock with the station moving at 28,000 kilometers per hour. A delay or failure in one supply mission can throw schedules into chaos. Now extend that to Mars, 225 million kilometers away, where a shipment could take 6 to 9 months to arrive, with launch windows opening only once every 26 months. Suddenly, the chain becomes not a lifeline, but a thread stretched to the breaking point. An off-world colony would need almost everything from Earth, at least for the foreseeable future: food, medicines, replacement parts, electronics, clothing, even simple tools. The machines that recycle air and water would require maintenance and replacement components. The solar panels powering habitats would degrade under the relentless Martian dust. Filters would clog, seals would wear out, batteries would corrode. Even the smallest defect, a torn glove, a leaking valve, a cracked visor, could become fatal without spares. And spares don't grow on alien soil. They come from home. The romantic image of a self-sustaining colony sounds appealing, but it collapses under scrutiny. Mars has resources, yes, ice, minerals, even carbon dioxide for fuel, but extracting and refining them would require entire industries. Mining equipment, refineries, chemical plants, and manufacturing lines would all need to be transported from Earth, along with the specialists to run them. Building such infrastructure from scratch on a dead world would take centuries and consume more energy than the colony could ever produce on its own. In the meantime, every critical resource, from medical supplies to microchips, would have to be shipped across the void. And space, as we've seen, is not a friendly courier. Launch failures happen. Solar flares can disrupt communications. A single collision with orbital debris can destroy a spacecraft. Every shipment would face countless risks on its journey, any one of which could mean disaster for those waiting on the other side. If a supply ship were lost, economic or environmental turmoil on Earth interrupted launches, an entire colony could be left stranded. Without new materials and maintenance supplies, life support systems would slowly degrade, power would dwindle, and survival would become a countdown clock ticking towards zero. We already know how fragile such systems can be. The ISS has experienced numerous close calls, coolant leaks, electrical failures, and fires. Each a reminder that even a minor malfunction in space can escalate quickly. But those astronauts have the luxury of escape capsules and rescue missions. Mars colonists would not. They would be 200 million kilometers away, utterly alone, with no possibility of evacuation. If their resupply chain faltered, they would die where they stood, surrounded by technology that could no longer sustain them. Even if the logistics worked perfectly, the economics would be staggering. Every kilogram of cargo launched into orbit costs tens of thousands of dollars. Shipping even small payloads to Mars would multiply that cost exponentially. A single colony of a few dozen people could require thousands of tons of supplies every year, not counting the spacecraft, fuel, and infrastructure needed to deliver them. That means trillions of dollars annually, sustained for generations, to maintain a settlement that could never feed or clothe itself without Earth's help. And there's a psychological dimension to this dependency. Imagine knowing that every bite of food you eat, every breath of air you take, every tool you use was sent from a world hundreds of millions of kilometers away. A world you can see in the night sky, glowing faintly blue, forever out of reach. One missed delivery, one global crisis on Earth, one broken rocket fleet, and the illusion of freedom collapses. We like to think colonization means escape, a way to start over, to live beyond Earth's mistakes. But in truth, every off-world colony would be a satellite civilization, tethered by fragile logistics to a world it cannot survive without. Space doesn't offer independence, it magnifies dependence. On Earth, we have redundancy, ecosystems, economies, millions of skilled people, and billions of tons of resources. In space, there is none of that. One factory, one power system, one food source, one failure away from extinction. This fragility exposes a deeper truth. Our dream of colonization isn't about expanding civilization. It's about extending supply chains. And like any chain, its strength depends on its weakest link. History shows what happens when supply lines break. Ancient colonies on Earth, cut off from their homelands, withered and vanished. Space will be no different, except there will be no wreckage for future explorers to find, no ruins buried under sand, just silence. And even if we manage to build a flawless system, an endless flow of ships connecting Earth to Mars or the Moon, the cosmos has a way of reminding us that perfection is an illusion. Space is not empty. It's alive with hazards, asteroids, solar storms, micrometeoroids, each one capable of turning a thriving colony into a footnote in the dark. Because beyond logistics, beyond technology, lies something far greater and more merciless than any human error: the raw, unpredictable violence of the universe itself. Space, for all its silence, is far from still. It's not the serene void we imagine when we look up at the night sky. It's chaos, a ceaseless, invisible storm of debris, radiation, and celestial violence. The universe is alive with motion. Asteroids tumbling through the dark, micrometeoroids hurtling at unimaginable speeds, and solar flares erupting from the sun with enough energy to cripple entire worlds. Out there, survival isn't about courage or technology. It's about enduring a universe that doesn't even notice you're there. Every inch of the cosmos is filled with danger, and none of it negotiates. Take micrometeoroids, grains of rock or metal no larger than a grain of sand, traveling at tens of kilometers per second. In space, speed is everything. A collision at those velocities carries the force of a bullet, sometimes more. The International Space Station, orbiting just above Earth, endures constant bombardment from these tiny projectiles. Its hull is layered with special shielding designed to absorb or deflect impacts. But even then, astronauts occasionally hear sharp pings as dust-sized objects strike. One breach, one puncture in a habitat wall, could decompress an entire module in seconds. Now imagine a Mars-bound spacecraft, months or years from any help, traveling through the asteroid belt, carrying humans in a fragile shell of aluminum and composite material. Every millimeter of that hull must hold, every second of the journey. There's no repair shop, no emergency exit. If a micrometeoroid penetrates even a small compartment, the resulting decompression would be catastrophic. The astronauts wouldn't hear a sound. One moment, they'd be alive. The next, the atmosphere around them would vanish. And that's just the small stuff. Larger debris, fragments of defunct satellites, spent rocket stages, or natural meteoroids represent an even greater hazard. Space isn't empty. It's a junkyard. Low Earth orbit alone contains over 36,000 tracked objects larger than 10 centimeters and millions more too small to monitor. Each piece travels at about 28,000 kilometers per hour, fast enough to tear through steel. A single collision can generate thousands of additional fragments, a chain reaction known as the Kessler syndrome, a self-perpetuating storm of debris that could render Earth's orbit unusable for decades. Even now, satellites and space stations must occasionally perform evasive maneuvers to avoid impact. As we send more missions into space, this risk only grows. Beyond debris, the real monsters are celestial, asteroids and comets that wander the solar system like cosmic time bombs. Most are harmless, orbiting predictably between Mars and Jupiter, but some cross Earth's path, drawn inward by gravitational tugs. A rock, just a kilometer wide, if it struck Earth, could erase a continent and plunge the world into years of nuclear winter. On a smaller scale, such an impact on a colony or spacecraft would be instantaneous annihilation. Even a pebble-sized fragment moving at orbital velocity carries the energy of an explosive. We've mapped many of these near-Earth objects, but many isn't all. Thousands more remain undiscovered, their trajectories uncertain. The universe doesn't send warnings, only impact craters. For a colony on Mars, or a station in deep space, there would be no defense, no atmosphere to burn incoming objects, no oceans to absorb shockwaves, just direct, unfiltered destruction. And then there's the Sun, our life-giver, and our most unpredictable enemy. Solar flares and coronal mass ejections hurl billions of tons of charged particles into space, creating electromagnetic storms that can knock out satellites, disable electronics, and bathe astronauts in lethal radiation. On Earth, our magnetic field deflects most of it. But in space, far from that shield, exposure can be deadly. During a major solar event, radiation levels can spike to 100 times the normal rate, enough to cause acute radiation sickness in hours. A single, powerful solar storm could wipe out communication networks, fry electronics, and disable life support systems in space habitats. On Mars, where there's no magnetic field, surface radiation from a solar flare could exceed the fatal dose many times over. Colonists would have to take refuge underground or inside heavily shielded bunkers, waiting days or even weeks for the radiation to subside. These aren't rare occurrences. Solar storms happen regularly, following the Sun's 11-year activity cycle. The last major one to hit Earth in 1859, known as the Carrington event, caused telegraph wires to catch fire. If a storm of that magnitude struck today, it could devastate our global infrastructure. Imagine what it would do to a fragile outpost on another planet. And if the sun is not enough, the cosmos itself poses its own relentless threats. Gamma-ray bursts, the death throes of massive stars, can release more energy in seconds than our sun will emit in its entire lifetime. They're rare, but if one occurred within our galactic neighborhood, it could sterilize entire planets, stripping away atmospheres and leaving only scorched rock behind. Space isn't just dangerous, it's indifferent. It doesn't hate us. It doesn't even know we exist. Even our technology, advanced as it is, cannot fully protect us. Shielding helps. Early warning systems help. Redundancy helps. But everything has limits. You can't armor a spacecraft against every particle or build colonies deep enough to hide from every cosmic event. To live in space is to live on borrowed time, surrounded by a universe that operates on scales of energy and destruction far beyond our comprehension. It's ironic. We dream of leaving Earth to escape risk, to ensure our species survives whatever catastrophe we might cause here. But the moment we step beyond our atmosphere, we enter a realm where the risk is infinite and mercy non-existent. Every second, our survival would depend on flawless machines, perfect timing, and blind luck. One cosmic hiccup, one flare, one stray rock, and everything we've built could vanish in an instant. And beneath all those dangers lies a quieter truth, one that no amount of technology can solve. Even if we somehow survived the asteroids, the flares, and the debris, even if our ships held together and our colonies endured, there's one enemy we can never escape: our biology. Every cell in our bodies, every process of life, every rhythm of our existence is tied to Earth, to its gravity, its air, its microbes, its sunlight. Out there, in the alien dark, we are not just fragile, we are out of place. Every atom of us belongs to Earth. From the calcium in our bones to the oxygen in our blood, from the microbes in our gut to the light that calibrates our circadian rhythms, every part of our biology is the product of 4 billion years of evolution under one set of conditions, conditions that exist nowhere else in the known universe. We are not merely on Earth, we are of Earth. Every cell, every molecule, every heartbeat carries the signature of this planet. To leave it is not just to travel, it's to defy the environment that made us possible. It's easy to imagine that humans could simply adapt to space, that our bodies could adjust to alien worlds the way they adjust to new climates or altitudes. But those differences are trivial compared to what awaits us beyond Earth. Everything about the cosmos is incompatible with life as we know it. Our lungs depend on the exact mixture of nitrogen and oxygen that surrounds us. Our skin relies on the gentle balance of ultraviolet light filtered through our atmosphere. Our immune systems evolved in harmony with trillions of microorganisms that live on and within us. Gravity shapes not only our posture, but our blood flow, our muscle tone, even how our cells divide. Remove or alter any one of those factors, and the delicate equilibrium of the human organism begins to unravel. Consider gravity, the constant, silent force that has pressed on every living creature since life began. On Earth, it dictates how our bones grow and how our hearts pump blood. In microgravity, that invisible scaffolding disappears. Without it, our bodies lose definition. Muscles waste away, bones thin, organs shift. Even at 1/3 gravity, like on Mars, scientists aren't sure if human biology can remain stable over generations. Then there's air, not just the gases themselves, but the pressure, the humidity, the molecular texture of it. Every breath we take on Earth is part of a cycle that connects us to the planet. The exhaled carbon dioxide that feeds plants, the oxygen they give back, the microscopic particles that remind our immune systems how to recognize threats. In a sealed environment, no matter how advanced, that cycle becomes artificial. The air grows stale, the microbial ecosystem collapses. Even if we purify it chemically, something ineffable is lost. The subtle complexity of a living biosphere that can't be replicated in filters or tanks. Microbes, too, are an inseparable part of us. Our bodies are not singular organisms, but symbiotic ecosystems, with more bacterial cells than human ones. These microbes regulate digestion, immunity, and even mood. But they depend on the biodiversity of Earth. Constant exposure to soil, air, food, and other organisms to maintain balance. In sterile space habitats, that relationship begins to falter. Some microbes die off, others mutate or become aggressive. Already, experiments on the International Space Station have shown that bacteria grow faster and more resistant to antibiotics in microgravity. Even the smallest organisms know where they came from, and they too begin to rebel when separated from home. Light is another forgotten necessity. On Earth, sunlight isn't just illumination, it's information. It regulates our circadian rhythms, triggers vitamin production, and affects our mood and cognitive function. The quality of sunlight in space, or on Mars, is alien. The day-night cycles are shorter or longer, the color spectrum altered, the radiation unfiltered. Artificial lighting can mimic some of these patterns, but never perfectly. Over time, this mismatch disrupts hormones, sleep, and mental health. Our brains, wired for the rhythm of terrestrial days and nights, lose their bearings in the eternal dusk of artificial habitats. Even the soil beneath our feet, something we rarely think about, plays a role in our survival. The microbes in it help generate nutrients in our food. The minerals it contains enter our bodies through crops and water. In space, we must simulate soil, engineer plants, and recycle every molecule. But synthetic systems lack the self-correcting balance of nature. A single mistake in chemistry, a single missing microbe, and entire agricultural systems can fail. On Earth, nature adapts. Off-world, we must predict every variable perfectly, forever. It's not that humans can't exist away from Earth. We can, temporarily. We've proven that in orbit, on the Moon, and through decades of research. The problem is that we can't live there, not in the full biological sense. Life, as it exists here, is interdependent. The air we breathe, the water we drink, the microbes in our bodies, the pull of gravity, they form an invisible web that sustains us. Cut one strand, and we can survive for a time. Cut them all, and the web collapses. Even if we could survive indefinitely in a sterile, artificial habitat, would we still be human in the same way? Or would we become something else, synthetic, disconnected, an imitation of life adapted to the vacuum rather than the soil? The longer we live away from Earth, the more alien we become, not only to our planet, but to the very definition of life that evolved here. Mars-born humans might one day have different bodies, different metabolisms, even different microbiomes. And when they look at Earth, they might see not home, but a place as foreign and hostile as we once saw Mars. Our biological dependence on Earth is not a weakness. It's a testament to how deeply we belong here. We are the product of this planet's history, the sum of its air, oceans, minerals, and living things. To sever that connection is to remove the foundation upon which everything we are is built. Space may hold wonders, but it will never hold the systems that created us. No other planet has Earth's balance of chemistry, energy, and ecology, a balance so intricate that we're only beginning to understand it. And maybe that's the greatest irony of all. While we dream of escaping Earth, we are still trying to replicate its miracles with machines. We chase the fantasy of other worlds because we take for granted the one that already works. But as we'll soon see, this obsession with leaving, with conquering new frontiers, blinds us to a deeper truth. In trying to flee our dying home, we risk forgetting how to save it. There's a cruel irony at the heart of humanity's greatest ambition. The more we dream about escaping Earth, the less we seem to care for it. Our obsession with the stars has become a mirror, reflecting not our courage, but our denial. We speak of Mars as our plan B, of the Moon as a stepping stone, of the cosmos as our destiny. But beneath those lofty words lies an unspoken confession. We're searching for a way out because we're afraid to face what we've done here. The fantasy of leaving Earth isn't just about exploration. It's about escape. It's the comforting illusion that if we ruin this planet, we can always start over somewhere else. But there is no somewhere else. The more we learn about the universe, the clearer that truth becomes. Earth is not one planet among many. It's an anomaly, a cosmic miracle, a fragile oasis of balance and beauty in a desert of lifeless rock and burning gas. Every other world we've studied, from the scorched clouds of Venus to the frozen deserts of Mars, tells the same story: lifeless, hostile, empty. Yet instead of protecting the one world that nurtured us, we fantasize about abandoning it, as if moving house could save us from ourselves. We pour billions into designing rockets to reach barren worlds while forests burn and oceans choke on plastic. We celebrate billionaires launching joyrides into the stratosphere while entire ecosystems collapse under our feet. The irony is painful. We can't even maintain one planet, yet we believe we're ready to manage several. The same species that struggles to keep its air clean and its water drinkable thinks it can build sustainable colonies on worlds with no air or water at all. This obsession with space as salvation isn't progress, it's procrastination. It lets us shift responsibility away from the present. Why fix Earth's climate when we can dream about terraforming Mars? Why solve poverty, pollution, and overconsumption when the next great frontier will supposedly reset the clock? But Mars will not forgive us the way Earth does. There are no rainforests there to regrow, no oceans to cleanse the air, no resilient ecosystems to rebuild what we destroy. We treat this planet as disposable, yet it's the only one capable of sustaining life at all. Every environmental crisis we face, rising seas, melting ice, mass extinction, is a warning that Earth's balance is not infinite. Yet, instead of learning from these warnings, we repeat them elsewhere in imagination. Terraforming Mars is often presented as a heroic project, a testament to human ingenuity. But the irony runs deep. We are already terraforming Earth unintentionally through pollution and carbon emissions. The difference is that on Mars, we fantasize about creating life, while here we are actively unmaking it. It's not that dreaming of space is wrong. Curiosity is what defines us. The desire to explore is noble and deeply human. But when that dream becomes an excuse to ignore our home, it turns toxic. The stars can inspire us, but they cannot save us. For every dollar spent on rockets, imagine what could be done to heal the planet beneath our feet. To restore coral reefs, replant forests, develop sustainable energy, and protect the countless species that share this fragile biosphere. The technology that could one day take us to Mars could, today, save Earth. But our priorities are skewed by spectacle, by the romance of leaving, not the responsibility of staying. The environmental mirror of space exploration reflects who we are and what we fear to admit. When we look at Mars, we don't see the future. We see a warning. A once living world, stripped of its atmosphere, dried to dust, its rivers long vanished. A world that may have been vibrant once, but is now silent. In that silence, we glimpse our own reflection. Earth could become Mars if we continue to forget that life is not guaranteed, that balance can be lost. We stand at a crossroads. The choice before us isn't between staying or leaving. It's between renewal and ruin. Space will always be there, waiting. But Earth will not wait forever. Every year we delay, every forest burned, every glacier lost, every species erased, brings us closer to the fate we so arrogantly imagine escaping. There is no spaceship large enough to carry 8 billion people. There is no planet ready to replace this one. If anything, our journey to the stars should remind us of how rare and precious Earth truly is. The photos taken by astronauts, Earthrise, the pale blue dot, changed humanity's perspective not by showing us the stars, but by showing us home. From space, there are no borders, no divisions, only a fragile sphere of blue and white, suspended in darkness, holding everything we have ever loved. That's the paradox of our cosmic ambition. The further we look outward, the more we should realize what we're at risk of losing. Our fascination with space shouldn't distract us from Earth. It should humble us, because the more we learn about the universe, the clearer it becomes that there's nothing else like this. Nowhere else to go. No other cradle to fall back into. And yet, even if we somehow manage to repair the damage, even if we learn to live sustainably, to protect the world that made us, there's something deeper still that binds us here. Beyond biology, beyond survival, beyond physics, there is a pull that no rocket can escape, the emotional gravity of home. There is something in us that knows, instinctively and without reason, that Earth is home. It's a truth that exists deeper than thought, an emotional resonance woven into the fibers of who we are. Every sunrise, every gust of wind, every scent of rain on soil speaks a language that our bodies and minds understand on a level that no science can replicate. We belong here, not just biologically, but spiritually. And that bond, that sense of belonging, is something no other planet can ever offer. When astronauts leave Earth and look back at the blue sphere suspended in darkness, many describe a feeling that no word quite captures, a mix of awe, longing, and recognition. Some call it the overview effect, a sudden, overwhelming awareness of Earth's fragility and unity. They see the planet not as a collection of nations or borders, but as a single living organism, vibrant, fragile, breathtaking. That moment often changes them forever. But it also reveals something profound. The further we go from Earth, the more we realize how much of us is still tethered to it. It's easy to imagine that home is simply a place where we live, but it's more than geography. It's the sound of waves against a shore, the smell of trees after rain, the color of a sky that deepens from gold to indigo. It's the chorus of life, insects, birds, rivers, laughter. On Earth, we are surrounded by a symphony of familiarity that we didn't just grow up with, we grew from. Our senses evolved for this world. Our eyes are tuned to the exact wavelengths of sunlight that pass through our atmosphere. Our lungs crave the balance of gases in this air. Our ears are shaped to hear the frequencies of nature, the wind, the voices of others, the heartbeat of a living planet. Imagine standing on Mars, beneath a pale pink sky. The horizon stretches endless and silent. There is no sound, no rustling leaves, no distant call of life, only the hollow hum of machinery. You can't feel the air on your skin because you're encased in a pressurized suit. You can't breathe, can't touch, can't smell the world around you. The surface beneath your boots isn't soil. It's sterile dust, sharp and lifeless. Even the light feels wrong. Too thin, too cold, filtered through an alien atmosphere that turns the sun into a dim ember in the sky. Mars may look beautiful from afar, but it would be like living inside a photograph. Static, distant, disconnected. Home isn't just about survival, it's about belonging. And belonging is built from memory, emotion, and connection. Earth is more than where we came from. It's what we are made of. The rhythm of waves, the pattern of seasons, the smell of forests. These things shaped our cultures, our myths, our sense of time and meaning. Every civilization, from the dawn of humanity, has defined itself through its relationship with the natural world. The constellations guided us, the rivers fed us, the mountains inspired us. We sing about them, write about them, build our lives around them. No barren world could ever replace that. Even if we built perfect domed cities on Mars, filled them with parks and artificial sunlight, there would still be something missing, something subtle but essential. The feeling of being part of a living world, the knowledge that outside the window, life thrives in infinite forms. On Earth, even when we are alone, we are never truly isolated. The hum of existence surrounds us. On another planet, we would live inside bubbles of survival, cut off from the ecosystem that defines our sense of reality. The silence would not be peace, it would be absence. And there's another truth we rarely admit. Our idea of home isn't just about comfort, it's about identity. To leave Earth entirely, to live on another world, would change what it means to be human. Our history, our emotions, even our psychology are bound to this planet's rhythms. We write poetry about the moon because we see it rise and fall. We feel awe at the ocean because we can stand at its edge. Without those experiences, what would shape our sense of wonder? What would root our stories? We sometimes imagine that humans could learn to love another world, that, given enough time, Mars or some distant moon might begin to feel like home. And maybe, in a purely physical sense, we could adapt. Maybe it's possible that something deep in their DNA, some ancestral whisper, would still long for the sound of rain, the scent of flowers, the warmth of an ocean breeze. This connection, this emotional gravity, might be the most powerful force in the universe for us. It's not measurable or material, but it shapes everything about how we see the cosmos. No matter how far we travel, we carry Earth inside us, in our blood, in our breath, in our dreams. Every song we sing of love, every story we tell of adventure, is, in some way, a story about home. And maybe that's why we keep looking outward. Maybe we're not trying to escape Earth, but to understand it, to see it from a distance, so we can finally grasp how extraordinary it is. The stars inspire us, yes, but they also remind us how small and sacred our world is in the cosmic darkness. We search for other worlds not to replace Earth, but to confirm what, deep down, we already know. There's nothing else like it. In the end, the need for home isn't a limitation. It's our compass. It reminds us where we belong and what we must protect. The tragedy is not that we cannot leave Earth. It's that we might forget why we shouldn't want to. Because the more we dream of the stars, the more we risk losing the very thing that made us dream in the first place. And as that realization settles, a new kind of understanding begins to form. One not built on escape, but on appreciation. The future of humanity may not lie in abandoning Earth, but in learning to live with it, to honor it, and to preserve it. Because the truth is, our destiny was never written among the stars. It was always written here, in the soil beneath our feet. For all our grand visions of interplanetary empires and thriving Martian cities, the truth is far more grounded, and perhaps far more human. The future of space exploration will not be about conquering other worlds. It will be about learning to exist just beyond our own. The romantic dream of colonizing the cosmos, of humanity scattering like seeds across the stars, belongs to the realm of imagination. The real frontier lies in building sustainable footholds near home, orbiting stations, lunar outposts, and fleets of robotic explorers venturing into the unknown on our behalf. This isn't a failure of ambition, it's a recognition of reality. We are not built for deep space, and the universe was not built for us. But that doesn't mean we stop reaching. It means we redefine what reaching looks like. Humanity's future among the stars won't come from mass migration. It will come from intelligent presence. Small, strategic, collaborative, machines extending our senses, humans working at the edges, and Earth remaining the center of it all. Take the International Space Station. It's not a colony. It's not even permanent. But it's a miracle of cooperation. A fragile machine kept alive by nations working together, orbiting 400 kilometers above the planet. It's taught us more about living in space than any science fiction ever could. It's also shown us the limits. Every system on the ISS depends on resupply, maintenance, and human vigilance. It's a glimpse of the best we can do right now, and a humbling reminder that living beyond Earth is an endless act of maintenance, not liberation. The next step isn't Mars, it's the Moon. Unlike Mars, the Moon is only 3 days away, close enough for real-time communication and emergency return. It's the perfect testing ground for sustainable living off Earth. NASA's Artemis program, along with international and private partners, is planning to establish a permanent lunar base, not a colony, but a research outpost. It will be a place to learn how to use local resources, generate power, grow food, and survive long-term in a hostile environment. The lessons from the Moon will determine whether humanity can ever go further safely, not just technologically, but psychologically and ecologically. And while humans explore nearby, our robotic emissaries will continue to go where we cannot. The rovers on Mars, the probes around Jupiter and Saturn, the telescopes peering into the deep past. They are already doing what we dreamed of doing. They are our eyes, our hands, our curiosity made manifest. These machines don't need air, food, or comfort. They can survive where we would die instantly. Through them, we've touched comets, landed on asteroids, and looked beyond the edge of our solar system. They are the true colonizers, not of land, but of knowledge. Our species is uniquely positioned for this kind of exploration, one that doesn't demand leaving home behind, but rather extends its reach. We can build orbital platforms that serve as way stations for research, industry, and communication. We can deploy satellites that monitor Earth's health and help us understand how to preserve it. We can send fleets of robotic explorers to every corner of the solar system, expanding human presence without risking human lives. And perhaps, one day, we'll construct massive habitats, spinning space stations with artificial gravity, gardens, and ecosystems of their own, orbiting peacefully between Earth and the Moon. Not colonies in the traditional sense, but human outposts within reach of home. That's the real future. Not planetary conquest, but stewardship. Instead of abandoning Earth, we can use space to protect it. Solar power collected in orbit could one day supply clean energy to billions. Mining asteroids could reduce the need to scour our own planet for resources. Satellites can monitor climate change, track deforestation, and predict natural disasters, giving us the tools to repair the damage we've done. Space isn't our escape from Earth, it's our opportunity to save it. For generations, we've looked at the stars and seen our destiny. But maybe destiny isn't about distance. Maybe it's about perspective. Every time we send a spacecraft farther from home, every time we capture another image of the pale blue dot, we're reminded of what we already have and what we stand to lose. Exploration, at its core, isn't about finding new worlds. It's about understanding our place in this one. And that's where the dream becomes something deeper. The future of humanity may not be scattered across planets, but connected through purpose, a civilization that learns to live within its limits, using the vastness of space to reflect on what it means to exist at all. The technology we build for the stars, sustainable life support, renewable energy, efficient recycling, may ultimately teach us how to live better here, on the only planet that truly welcomes us. The stars will always call to us. We will answer, but not by abandoning Earth. We'll answer by sending our creations, our intelligence, our curiosity. We'll orbit, observe, learn, and protect. Space will be our laboratory, not our escape hatch. And maybe, just maybe, that humility, that understanding of our place, is what the universe has been waiting for us to realize. Because once we stop trying to flee home, we might finally learn how to care for it. And perhaps that was the lesson hidden in all our failed dreams of colonization. That the purpose of looking outward was never to leave, but to understand why we should stay. And so, after all the rockets, all the fantasies, all the centuries of dreaming, the story comes full circle. We were never meant to be wanderers forever. The stars were never a destination. They were a mirror, a reminder of who we are and of the only place in the universe where we truly belong. In the end, after all the dreaming and all the reaching, after every rocket and every promise, we arrive at a quiet truth. One so simple, it almost feels like defeat, yet so profound, it might be the beginning of wisdom. Maybe the point was never to leave Earth at all. Maybe the purpose of our yearning for the stars has always been to remind us how precious, how singular, how irreplaceable our home really is. For centuries, we've looked to the heavens and seen our future there. Cities on Mars, ships gliding between stars, humanity transcending its cradle. But the universe has given us its answer, whispered through silence and distance. We are already where we belong. Earth is not a starting point, it's the destination. It's the culmination of 4 billion years of miracles, a world of balance so delicate, so perfectly tuned, that it sustains the impossible, life. Every breath we take, every sunrise we witness, every heartbeat that continues without effort. These are gifts no other planet has ever offered, and perhaps none ever will. We've spent generations imagining other worlds, but in doing so, we've forgotten to look closely enough at this one. We dream of painting skies over alien deserts while ignoring the fading blue of our own. We long to walk beneath foreign suns while we turn away from the forests, oceans, and rivers that have shaped us. We want to find another Earth, when the one we have is crying out for us to remember her. The truth is, there is no second Eden, no backup paradise, no other shore waiting for our escape. There is only here, only now. And perhaps that is the real meaning of our journey, not to conquer the cosmos, but to understand its silence. The stars remind us not of where we might go, but of how rare it is that we can live anywhere at all. We search for other planets with oceans and skies, but every telescope we build, every probe we send, returns the same message in different forms. There is nothing like home. Earth is not just another world. It is a masterpiece of chance, a symphony of physics and biology that came together once in a universe of endless emptiness. Maybe we were meant to reach for the stars, not so we could leave, but so we could finally see ourselves from a distance, to understand that what we've been searching for has always been beneath our feet. The further we look outward, the more we realize how extraordinary this small, fragile world truly is. From space, there are no boundaries, no nations, no divisions, only the shimmer of oceans and the swirl of clouds, a planet alive against the darkness. From space, humanity's noise fades, and what remains is pure perspective. We are caretakers of something irreplaceable. Every action we take, every decision we make, echoes across the only world that will ever sustain us. To harm it is to harm ourselves. To save it is to save everything we've ever been and ever will be. The dream of leaving Earth should never have been about escape. It should have been about appreciation, about learning what it means to be home. Because home isn't a place we abandon when it's inconvenient. It's a promise we keep. It's a bond between what we are and what made us. The stars may call to us, but their light is only there to guide us back, to remind us of who we are and how small acts of care here on this blue world are more meaningful than any distant conquest could ever be. In the end, maybe the lesson was never hidden in the stars at all. Maybe it was in the soil, the wind, the rain, in the rhythm of waves, in the simple miracle of breathing air that no machine had to make. Maybe the greatest discovery humanity can ever make is not another planet, but the realization that we already live in the most extraordinary place in the universe. So no, we may never truly leave Earth. And maybe that's not a tragedy. Maybe that's grace, because while the cosmos stretches on, cold and eternal, we are here, on a world that loves us back, a world that gives, that forgives, that shelters and sustains, a world that, against all odds, made life. The point was never to escape it. The point was to understand it, to love it, to keep it. Because this fragile, miraculous living planet is not just where our story began, it's where it was always meant to stay. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.